you want to. But number 9, what they want you to do, and this is going to be something we need to be able to do throughout the rest of the year. Because a lot of times they're asking us to evaluate functions, but they might ask us to essentially evaluate a function at another function, okay? Or through the use of inputting another function. So x plus 2 is ultimately another function, right? Okay. But what it means is that x plus 2 is what's in parentheses. That is what you are going to replace that variable x with. Okay, let's see if we get this working. There we go. Okay, and when you replace a variable with a quantity, okay, now that quantity, it's a little bit easier here to see that the quantity is, two objects, x plus 2. But even if it's just negative x, we refer to that as a quantity, okay? And you want to put that negative x in parentheses. You want to put x plus 2 in parentheses. You want to put whatever this thing is. And I even do it when it's just something like this, okay? Just a singular x. But put it in parentheses, because if there are exponents, it reminds you of what you need to do with those necessary exponents in that quantity. So if we go ahead and start substituting, okay, understand that when we go f of x plus 2, that means everywhere that I saw an x in the original function, okay, I'm now going to replace it with the x plus 2, right? Okay. So what I like to do is I like to just go through however many times I see the x, I just put in parentheses first, okay? And I block that region all a second, and I know I've got to put something in there, and now I'm going to put that x plus 2 in there. Okay. And what that tells me then is you have x plus 2, the quantity squared, times 4 plus 3. So order of operations, if we're going to simplify this, order of operations tells us we have to do that first. So that becomes x plus 2 squared becomes x squared plus 4x plus 4. We still have that 4 out front as a multiple. Okay. So we're going to run that through and get 4x squared plus 16x plus 16 plus then 3. And then combine like terms, which you get 4x squared plus 16x plus 19. I think what people miss a lot of times is that O and I term again when they FOIL that, or they just leave it as 4 times quantity x plus 2 squared plus 3. And to be honest with you, they tell you to simplify, but eventually that will actually probably be better for us because it's in a better format to graph. Okay, because when I look at that, I should know eventually, we'll talk about graphing quadratic equations, but we should know where the vertex is from that information. We should know if there's a vertical stretch from that information, that kind of stuff. So there's a horizontal movement, there's an up and down movement, which you don't really necessarily gain when we look at it in that form. But the task was to insert the x plus 2 and then simplify. The next one said find f of x plus f of 2. Okay? So f of x plus f of 2. So now, if I find f of x, which is 4, okay, I'm going to replace the x with x here, okay? It's kind of trivial in this case when I'm just replacing something with itself. So that's going to leave me just then 4x squared plus 3, right? Okay. The next part says find f of 2. Okay, so we found f of x already. Now we're going to find f of 2. So now 4, whatever my input value is squared, so in this case 2. Okay. And now I'm going to evaluate that. Well, 2 squared is 4 times 4 is 16 plus 3 is 19. So it evaluates to 19. Okay. Now, we have f of x plus f of 2. If I wanted to add those two things together, this is f of x, and that's f of 2. So we add those together, and we get 4x squared plus 22. All right. And the reason they ask you to do this, the reason they ask you with this question, is because they want you to recognize, and they don't necessarily ask this at the end, but they want you to recognize that f of x plus 2 does not equal f of x plus f of 2. Does that make sense? Okay. Which is a good piece of information to know that those are not the same. There will be situations in this course and other courses where they ask you to do maybe two different things to a function, two different operations, and they're kind of very similar to one another. You recognize that, I can get the same result looking at it two different ways. Does that make sense? Here, you do not get the same result by looking at it two different ways. So that's kind of a common type of problem that you might see. Does that help? Number 20 looks something like this, and this is just asking for domain values, okay? And the domain values, remember, those are the x values you're allowed to use. So initially, we're going to make the assumption that our domain is all real numbers, okay? But we know that with division and or square roots, right, it's even roots, okay? Square roots, fourth roots, sixth roots, that kind of stuff. There are algebraic issues, right? Okay. With division, you can never divide by what?
0.
0. So I'm going to take that expression, x squared plus x minus 56, and I'm going to tell myself that it cannot be 0. Okay? And if it cannot be 0, I'm going to solve that like an equation, but when I'm done, it'll be x cannot be this number and x cannot be this number, and that tells me basically what to kick out of my domain. So how does that factor? Yeah, 7 and 8, right? And 8's got to be negative, 7's got to be positive. Okay. Nope, sorry, I did that wrong there. Flip-flop it. Positive. Negative. Okay. So now, in this situation here, x cannot be negative 8, and in this one, x cannot be 7 once we solve those smaller equations, right? Yeah. So going back to kind of set builder notation, we would put a semicolon here and say x cannot be negative 8 or 7. Okay, so that would be one way of writing it. And I like to show that you're not going to type it into MathXL that way, but I like to show that so you know in some textbooks or other publications maybe that I provide you or PowerPoints, if they give you that notation, all they're saying, the way I read that, is x such that x belongs to the real numbers. Okay, so that's the only thing we're talking about is real numbers, no imaginary numbers here. Okay, so x is going to belong to any real number, or it's going to be any real number, except x cannot be negative 8, 7. So that's how you read that domain here. Now, as a number line, okay, we would have issues, like I said, at negative 8 and 7. So maybe negative 8 is there, maybe 7 is there. And we know that because x cannot be those, when we graph our solution, there should be open dots there, right? And that's the visual for telling us that there is no solution in that region. And then the rays or segments tell us then that those are acceptable values. So, you know, there's a segment between negative 8 and 7. So all the values in between negative 8 and 7 are acceptable values for x in this case. Okay. But now we have to put this in interval notation. Okay. So reading our number line left to right. Now you don't always have to do a number line, but the hope is that we start to visualize it in our minds, but we don't have to put it down. Right? We don't write it down. But I think writing it down initially might be a good idea for someone, especially if we're struggling with these. But what's the first number over here on the left-hand side that we're coming across as we read this left to right? Negative infinity. Okay? Put a parenthesis around negative infinity. And then we get up to the left-hand side of negative 8, right? But I cannot use negative 8. I'm saying that the first number on the left-hand side of negative 8 is acceptable, but negative 8 itself is not acceptable. So the only way I can write that is to use that notation. And that means a number like negative 8.000000, many zeros you can say in a 1, will be the first value that you can use. Okay? Obviously, it's impossible for us to write that first number to the left of negative 8. We have to write it out in decimal form. So we just say, well, we're going to look at negative 8, but the parenthesis says just the values to the left of negative 8. Okay, the first value to the left. Then we skip negative 8, and now we're going to use the first value to the right of it, right? So negative 7.999999999 forever. Again, not feasible, not logical to write that number out. So we write negative 8 with the parenthesis, and that identifies that first number to the right-hand side of negative 8. We then continue through, and what's the next issue? 7. Okay. For the same reason, we'd really be looking at 6.999999999, so we're going to write 7 with the parenthesis, skip over 7, and then continue through to the end, to infinity. And we have to union those three things, because what it says is that an x value can come from over here, or an x value can come in here, or an x value can come from there. Okay? And that will then provide some f of x value when I choose any x value from those three ranges. Okay. Maybe range is not a good word. Any x value from those three intervals. Okay. Is that doable? Okay. Very, very, very important that we understand that interval notation. Spend a lot of time talking about that because it's in the course a lot. Okay. A lot of things that we do, you're going to answer things like this. You're going to get theorems and some definitions and stuff like that throughout this course and your next course that use interval notation inside the theorem. Okay? If I don't understand what that means, I'm going to struggle with that theorem and being able to apply it. Okay? We have talked about this, but in this case, a lot of times we want to look at the numerator as well. The numerator is a power function, okay? And with a power function, your domain is all real numbers, okay? So that thing, there are no issues with that, so that's why we kind of neglected it to begin with. I don't know if I said this in your guys' class yesterday. I do know I said it in second period. If you watch the lecture from yesterday in second period, we talked about this. If I have some polynomial, it's called p of x, and we talked about a couple days ago that we can call this polynomial. You guys remember seeing this? Okay. Where a sub n minus 1, a sub 1, and a sub 0, they were just constants. Okay. But my n minus 1, my n minus 2, my power of 1, and my power of 0 for my x, those were integers. Okay. Positive integers. Okay. That's a polynomial. Anything in that form is polynomial. So something like 3x cubed plus 2x squared plus 5x minus 7, or something like 7x to the 6th plus 2x squared plus 8. Those are all polynomials, right? Okay. If I have a polynomial, the idea, hopefully you can recognize this, is no matter what I plug in for x, I can always look at that bottom one. I can take any number I want for x, plug it in, raise it to the 6th power, and get a number back, right? Now you take that number and multiply by 7 and still get a real number back, right? I can then add to that x squared again times 2 and still get a real number back, and add 8 and get another real number back, right? So every single x value you start with, if you plug it in these two locations, you still get a real number back. Okay? Well, if that happens there, it should also logically happen there, okay? Because I have no division by 0 and I have no square roots, okay? So anything that's in polynomial form is going to have a domain of all real numbers. And that's kind of a feature that we recognize about all polynomials. So if on WebAssign or a test or quiz, the question is, hey, what is the domain here? And I can recognize that it's a polynomial, quickly answer that question as all real numbers, and I go to the next one, okay? And that's kind of something we're going to talk about as we go through the year. Specific functions, specific types of functions, categories are going to share similar features, okay? Domains being one of those features, okay? So all polynomials will have domains of all real numbers, okay? And that's why when we look at this, I can look at that top one, that's a polynomial, okay? It's very simple, but it's a domain of all real numbers. This one here is a polynomial as well, so it has an initial domain of all real numbers. But when I put them together through division, though this one has all real numbers as its domain, it provides division by 0 when I collectively look both of them together. Does that make sense? And that's why we got those zeros. Okay. Are there any others you guys want to talk about? Christian?
Number 18.
18? and 12. Let's do 12 first. We didn't talk too much yesterday about the range, okay? And algebraically, it's really not the easiest thing to do to find range like we are algebraically finding domain, right? Okay. Finding the range right now for us is most likely easiest to do with just plugging values in, okay? And seeing what the smallest value that I'm able to gain when I plug x values in, and what the largest value I gain when I plug x values in, okay? So when it says find the domain and range of the function, okay? Well, the domain, what we call this, and we'll see this a little bit today in today's notes, that is a restriction. They're telling you that your graph is constrained to the values between 0 and 5. You cannot use any other x values. Does that make sense? Okay? So that is the domain. Okay? 0 to 5. They want an interval notation. So you see here, 0 is less than or equal to x is less than or equal to 5 is the domain. Okay? Initially, 3x squared plus 2 has a domain of all real numbers, right? But in any type of function that we ever want to deal with, we can just focus on any part that we want to. So for instance, let me pull up GeoGebra real quick here. If we look at is it 3x squared, is it plus 4? Plus 2. Okay, that's the function. That is the general 3x squared plus 2 without taking any restrictions. Does that make sense? Okay. Now, if I say I want to graph the same thing on top of it, 3x squared plus 2, I think this is the notation I have to use. Nope. Let's see. Nope. Wow. I'm not sure what the command is. I haven't used it in a while. But I should be able to take 3x squared and tell it I only want to use values between 0 and 5. It's not doing that. But if I only want to take values between 0 and 5, it essentially means you're not worried about x values to the left of the y-axis. Does that make sense? Okay. And I'm only really worried about values. Let's see if we can do this. I'm not going to be able to do it. I'm really only worried about, do it this way, values that come up to this vertical line here. Does that make sense? I'm only interested in this red curve between the y-axis and this line right here. Okay. So when we go through and we try to find the domain, it's already been provided in the restriction, but now with the range, we see that the range, if I read this bottom up, what's the first y value you come across for your range? It's 2, right? Okay. And then if I keep looking and I go all the way up, okay, so this thing's going to, I'm looking for that graph to intersect the line x equals 5, basically. And we see that that's going to happen right around 77, correct? Does that make sense? Okay. So those are the two values that we're looking for in regards to the range. Now, it's not always that easy. It's not always this easy, what I'm going to tell you right now. But basically with this problem, okay, because this is a parabola and it's been shifted up, the vertex is still on the y-axis, so we know the lowest point on this parabola is still on the y-axis. You can plug in 0 here for x, and you get f of x to be 2, right? Well, f of x is a range value, so when we choose our smallest domain value, we get our smallest range value of 2. So that's where that's coming from, okay? And if I plug in the largest domain value of 5, 5 squared is 25, times 3 is 75, plus 2 is 77, so we get f of x, or f of 5, is equal to 77, and that's where we're getting that largest range value. Okay, does that make sense? But what I want you, and right now, at least in the questions you saw on this assignment, that's what you can do, is that direct substitution to find the solution. But what I want you guys to understand is that eventually, we're not going to want to do that, because what if I end up having some function, let's just say x squared plus, let's go minus 4x plus 3. Something like that, okay? And I say, let's look at this thing from 1 to 4, okay? From 1 to 4. So I'm going to restrict the domain from 1, come on, let me write this. 1 to 4. So I'm just going to highlight the f of x values that I get back, maybe. If I highlight the f of x values from 1 to 4 for my x values, okay? So my domain, I'm going from 1 to 4, but now my range, okay? This is where if I plug in 1, I'm going to get 0 back, right? Okay? Is 0 the smallest y value that I have on that graph? That's my smallest y value there, isn't it? Okay? So finding a range by just simply plugging in the first domain value and plugging in the last domain value isn't the safest thing to do in general, okay? Because it's not going to give you every single time the smallest y value and the largest y value, okay? And as we move throughout the year, we will figure out maybe better ways of determining that range. But what I suggest that you do, if they ask you to find the range, use some technology to graph that function and then look at the graph and help you determine your range on that graph right now. Okay? It's pretty hard to analytically or algebraically find a range value. Okay? 18. This will be the last one we do, and we can talk about some more tomorrow. But 18, ooh, it's ugly. All right, x plus 4 squared. That's a power function. It's polynomial. Okay? So that numerator, I can plug any number in for x, add 4 to it squared, and still get a number back, right? You can take any real number and still get a real number produced. So the numerator doesn't affect this problem at all. Okay? There's no domain issues with the numerator. But when I look at the denominator, okay, the domain x such that x is an element of all real numbers, but now we're going to have to kick some stuff out because of that denominator. What kind of numbers can you take the square root of? Positive numbers and 0. Okay? So initially, we're going to say that that denominator, square root of 2x minus 1, has to be greater than or equal to 0. And I say initially because this is a special place where the square root shows up. When the square root shows up underneath, in the bottom of a fraction, or the denominator of a fraction, we cannot incorporate that 0 right there. Does that make sense? Because you can take the square root of 0, but what's the square root of 0? 0. So if I go ahead and solve this, okay, and we come up with, square both sides, equal 2x minus 1, add 1, I get x to be a half. Okay? That would be fine. If I just had just radical 2x minus 1, x being 1/2 is okay because I can plug that in and I get square root of 0, right? Square root of 0 is 0. So if that was in the numerator, no issue there. But because it's in the denominator, I'll have, 1/2 plus 4 squared up top. But when I plug in 1/2 right there, I get 0, right? So I get a number up top divided by 0, and that's undetermined, right? Or indeterminate, right? Okay, or undefined. So you can't do it. So what you have to pay attention to is just that slight change in the problem. And really, it's going to change my bracket to a parenthesis when we're done, right? Okay.
Wouldn't the -1 not make it a 0? It would make it a negative number. If x was 1/2, the 2 would make it.
Right, make it 1, right? So 1 minus 1 would give me that 0. Square both sides. Okay, add 1. Divide by 2 is going to do that at once. So x has got to be greater than 1/2. Okay. Anything less than that, you can start to see less than that. If x was 0, I would get a negative underneath the square root, right? And I would bring in imaginary values, and that's not what we want. Okay, when we graph f of x, and we're looking for these range values, they have to be real numbers. Okay, it's kind of what we talk about with the functions. That we input a real number, we get out a real number. Okay, so that would be a problem. That's why we don't choose any of those negative numbers. Okay, or numbers less than 1/2. And 0 would be another point that we, 1/2 being a point that we plug in, or an x value that we plug in. That would also provide an issue in that denominator. So that solution of x being greater than 1/2 makes sense, hopefully. And then if it's greater than 1/2, that's where we start with. We get to infinity, and now the issue is that needs to be a parenthesis.
So why don't you start with
Because it's not, you can FOIL that out if you want to. So you get x squared plus 8x plus 16, right? There's nothing wrong with doing that, but that becomes a polynomial. And that is, no matter what x value you plug in, you can square it and get a number back, right? You're going to add 8 times that x value, get a number back, and you can add 16, you still get a real number back, right? At no time, no matter what x value I choose in that numerator, I will never get back an imaginary number, and really that's all I got to worry about in that numerator.
Is it the same with the big 15 denominator, or?
Yeah, if it was in the denominator, if it was x plus 4 squared in the denominator, I would just want to make sure x plus 4 squared does not equal 0. So I'd go through and it'd be x plus 4 and x plus 4, so x would not be able to be negative 4, and that would be the value that I kick out.
Okay. You don't understand with the square root why you're saying that with an equality.
Because if I have if you just have a regular function f of x, okay, let's go with 2x minus 1 again, okay? We're saying that when we have domain values, we're looking for the x values, okay, x values that become input values, and they should spit out output values, right? The input value should be a real number, so anything off the real number line, okay? The output value should also be a real number, okay? Now, if I plug an input value in, that's a real number, but the output value that comes back out is an imaginary number, that initial input was a domain problem. Okay, it was a domain issue. So, and the way I determine that is I know that you cannot take even roots of negative numbers, right? Because that incorporates an imaginary quantity. So we need to force the radicand to be a positive, and really maybe the best way to say it is a non-negative number. So make it equal to 0 or greater than 0 in this situation. So if I solve that, I get x to be greater than 1/2, greater than or equal to 1/2. Okay? And again, writing that interval notation like this, but here's the logic behind that. If I choose any one of these values that's between 1/2 to infinity, I'm going to plug it in here. Okay? Just think about a number you plug in. Plug in, see if there's an easy one. Plug in 5. Okay? 2 times 5 is what? 10 minus 1 is 9 squared root of 9 is 3. So you plugged in a real number 5, got back a real number 3, right? Okay? Choose a number that's not in this interval of 1/2 to infinity. So if I choose in or plug in negative, let's try negative 4. Okay? If I plug in negative 4, that's a real number, right? What's negative 4 times 2? Negative 8 minus 1, negative 9. What's the square root of negative 9? 3i. 3i, that is not part of the real number line. Okay? So this number here needs to be excluded from my domain because it provided a non-real solution or non-real output.
So you'll always set it to greater than or equal to?
Yes, yes. But if it's in the denominator, it can't be equal to, it has to be greater. Okay. Let's talk real quick because we don't have a whole lot of time here, but let's get started on it.